Hello and welcome to Beamer Folk. I thought I'd introduce you to my explorations in choppers, specifically a chopping DC amplifier. Now, before I move into the block diagram of what's before you here, just a little brief explanation of chopping technology. We're probably all mostly familiar with the buck boost type power supply chopping technology, the advantage of that being efficiency, little heat dissipation, and the fact that it can transform the input to the output, similar to a transformer, an AC mains transformer, in the sense that you can have a high voltage on the input with a low source current or lowish source current, and that can transform using this remarkable technology into a low voltage on the output, but a very high current. We're kind of familiar with that technology. In amplifier, audio amplifier technology, of course, we're very familiar with, I should imagine most of you are familiar with Class D type amplifiers, and they are similar in a way, in the sense that the great advantage of a Class D audio amplifier is that it's very efficient, so therefore you don't need the heat considerations within the amplifier, and for example you don't need a largish heatsink, so there are advantages in cost. Up until fairly recently, about 5 years ago, the frequency response wasn't terribly good on Class D amplifiers, and there was always a kind of residual hiss, but modern Class D amplifiers are and can be superb. No, my exploration here is really quite an ancient art form, and that is that it's based on a need to amplify in a precision way to deliver a DC output for perhaps motors, calibrators, that sort of thing. And the circuit you have before you is a very simple, perhaps unrefined circuit that does that. And I'll move now into the block diagram. Well, the reason why this circuit exists at all is that if you have a input reference voltage which is very low, say 100 millivolts, but your output voltage, the required output voltage for that 100 millivolts, needs to be, say, 10 volts, there is 100-fold gain in that definition. And if the 100 millivolts on the input, which is your desired precision 100 millivolts, happens to be riding on, let's say, a DC offset of 1 volt, then your output required 0 to 10 volts would now be sitting on 100 volts. So there needs to be, and there are a couple other side issues in there as well. So therefore you need to somehow retain the precision of the 100 millivolts whilst isolating it from the unrequired 1 volt. The other couple of considerations that need to be thought about here is to do with temperature drift. And that is, if your source precision voltage has a certain drift and the gain between the input and the output is 100, then that thermal drift per degree C will also be multiplied by 100, and that's to be avoided. The other thing to take into consideration is aging, and that is that your input precision source might have a different aging characteristic to your times 100 amplifier. So all in all, it's very wise to kind of isolate the input from the output. You could think of it as a type of transformer. Now, the block diagram shown here is of my circuit I just showed you. And I'll go through it block by block and see what you make of it. But in principle, the isolation is achieved using two capacitors. One capacitor here called C in and another capacitor here called C out. And that naturally isolates the output from the input. But you need a bit of circuitry around this, indeed switching circuitry around this, to make this operate correctly. So the first block here is using the TL431 reference. You could incidentally use a much more precision reference than the TL431, but that is for my purposes what I use. I could have used a Zener diode, but I've got these lying around, so I used one. The next block you can see is a Mosfet chopper, and I've called it here the first chopper. And you have in the next block, post C in, a very simple AC amplifier, rather crude by comparison with the rest of the circuit, but that is what can be achieved here. And in the next block here, there is a second chopper, and these two work together, as it were, in harmony with each other around this simple amplifier. The only clause that is placed in this relationship between these two choppers is that they are operated by, via their gates at 180 degrees apart. That is, when that one is on, that one is off. When that one is off, that one is on. And my circuit uses a 10 kilohertz oscillator, which I use an E555 for that, a CMOS version of that, and a divide by 2. Well, that was a 4013. And I produced a separate video for that interesting little circuit. And I'll indicate that in the description below, and there should be a link to it coming in on the video here. And as you can see, you've got on the output there two phases. This when one is on, the other's off. When one's off, the other one's on. Here and here, and they drive those two choppers. Well, the result of that, and this output here can be considered and thought of as a synchronized rectifier. And it produces a series of positive chopped pulses at this point here, whereupon it goes into an integrator, which integrates those pulses, or you could consider it as a low-pass filter, into a constant DC voltage. The voltage on the output is not my required 0 to 10 volts DC. It is actually a lower voltage. So therefore, on the final output here, which is the last block, I've got a variable gain to boost that very low voltage from 0 volts to 10 volts DC. And that's effectively it. It's quite fundamentally a simple circuit, and used to be used a lot in electrical systems, electronic systems, back in the 60s and 70s. Once you start moving into the 1980s and 90s, DC amplifiers, integrated circuit amplifiers and DC amplifying blocks became much more precision. So the need for this type of structure has diminished. But nevertheless, there still are niche areas where this type of system is still employed. And now I'll move back to my circuit diagram, and you can see how I translated these blocks into an actual circuit on a breadboard. Right, here we are back at the circuit diagram of my chopper DC amplifier. It is the online simulation package from falstead.com. Excellent it is too. Not that I'm paid to say so. It's just my preferred simulator. To begin with, on the input here, 10 kilohertz clock, and the negative supply for the op amps over here, we obtained those via a 555, and that was the subject of another video which I've mentioned before, but I'll just include another link to it. But anyway, we have a square wave coming in here, approximately 50% duty cycle, although that's not critical, but for the power supply it was, going straight into a divide by 2, which is here, and that's the 4013 D-type flip-flop, the output of which, Q and Q bar, go into the chopper N-type MOSFET. This is MOSFET 1, that's MOSFET 2. And as we discussed, they are 180 degrees apart. When one is on, the other one is off. And they are the central core of this circuit. You have here the TL431, which is producing approximately 2.5 volts DC. That's going into a resistor, and on the other side of the resistor, that 4K7, it's being chopped by the MOSFET. The capacitance of the drain of both these MOSFETs are quite important. And I put a link below as to the MOSFETs I use. I obtained them from eBay, they're readily available. But you can't have too much capacitance there because it will affect the rise and fall time of the chopping. And the chopping trace for this is the first MOSFET here, this one here. These traces are slightly out of order. I wasn't able to get them in logical order. This simulator doesn't seem to provide that feature. It'd be nice to sort of realign these so that they follow the logical flow of this diagram, but it doesn't. This is the drain of the first MOSFET, and as you can see, you've got a 50% duty cycle, 2.396 volts DC being chopped, and that signal is going into the first capacitor, which, as you remember in the block diagram, was called C in, and that is another essential part of this chopping technology. The second capacitor, C out, is here, and stuck in between is a rather simple but critical AC amplifier. As you can see, it's a common emitter, single transistor, and it's operating at a gain that is quite low, 1.5. In fact, I had a bit of a job getting the gain down that low from this circuit, but I use a degenerative resistor here, that 3.9K, and a bit of feedback, localized feedback, which are these two resistors, the 82K and the 56K. You've got a bias resistor here of 100K, and that facilitates for a high impedance. Otherwise, the impedance going into the base of this transistor would be quite low, and that would load down this chopping signal here. Because remember that you've got a 4K7 here. So if this were a low impedance, it would it would affect, and in fact it still is affecting it very slightly, but it would effectively pull this chopping signal down. So I've managed to achieve an input impedance on this simple little AC amplifier of about 73 k ohms. And anyway, the output signal here, which is from the collector going into capacitor C out here, is the trace, this trace here. And we discussed that if you have 100 millivolts riding on 1 millivolt and you amplify it, you end up with 1 volt riding on 10 volts. In other circuits, that offset would be in this system here, but the way I've got this configured, the TL431 reference itself to ground, whereas the signal on the output of the collector here, if you look at it here, is riding on 8 volts. So our precision reference signal is actually this green signal here, and that is the precision bit that you're after. You're not after the DC voltage that it's resting on of 8.37 volts. And with the gain of 1.5, the amplitude of this would be, getting my calculator, the actual AC signal from peak to peak of this square wave is 11.603 minus the 8.037, which equals 3.566 volts. So that signal here is 3.566 volts. That signal is going via the capacitor C out into the second chopping Mosfet. And with the coordinated dance, if you will, with the first Mosfet driven by the divide by 2 Q and Q bar, that signal here, incidentally, they're 5 kilohertz because this is still operating as a divide by 2. You've got 10 kilohertz on the input, you would have 5 kilohertz on the output. So that is again being chopped. And this circuit here, this second Mosfet, is acting as a synchronized rectifier, referencing the rectification instead of with an offset voltage that you'd normally get with a diode. This is pulling this down to ground, and it's pulling a 10k resistor, which is this one here, down to milliohms. So it's a very good chopper, and you're removing any form of offset that would be created by using diodes. And that is, so this is the drain of, the second Mosfet, which is this trace here. And you can see this clearly illustrated. You've got ground here, and there's virtually no offset voltage there, to a maximum here of 1.562 volts. The amplitude of this second Mosfet, the 1.562, is of course lower than the signal we were getting at the collector of the transistor, which was here. And that is simply because the input to the next section, which is the integrator stroke low pass filter, the resistors here and here that are in parallel are drawing the value of the peak voltage being chopped down. There are two resistors in parallel here because this simulator is actually simulating the final circuit that I'll show you on the breadboard in a moment. So we move into the next section, which is the integrator itself. Well, that is converting the pulses through to a DC voltage effectively, it's smoothing it out. So the capacitor in the integrator here is this capacitor here, this 100 nanofarad here, and across it is a 100k resistor. That needs to be there because when the integrator doesn't have a signal to process, of course, an AC signal, it's at DC rest. And if you didn't have a resistor across from the negative input to the output of this op-amp would be an open gain situation. It would be saturated either to the positive or the negative. So it's important to have that resistor there. And of course, that under DC conditions defines the gain of this op-amp. That's op-amp A. And the gain of that DC gain here is 6.39. And of course, that value is derived from this resistor being derived by the paralleling of these two resistors. The output of which I don't have a trace, but it is a low-level DC voltage. And incidentally, because the positive DC coming in here is being inverted, the output would be negative. So you've got this DC voltage set into the negative realm. Let me just put this on here, and you can see that it's about -4. Let me put that on, -4.9. So you've got more or less -5 volts at the output of op-amp A. Now then, that goes into a simple DC amplifier output stage, which is op-amp B. And what that does is it inverts again the negative to a positive because you're in the negative input of the op-amp, and it operates the control of gain that you can derive from the whole of this circuit. And the output voltage here of op-amp B is this trace here. And as you can see, it's at 5 volts. The gain is, of course, derived from this resistor here divided by the paralleling of these two resistors here. So you've got at the moment 50k divided by the paralleling of 470k and 56k. This resistor here has a very small capacitance across it to iron out, integrate any small minor voltages that might rest on the output of op-amp A. The resistor here, which is 50k, I've brought out to a variable here. And at the moment, the variable is set at 50k ohms. That is producing 5 volts here. If I were to increase this to 100k, the output would be 10 volts. Let's just do that. So here we are. I've moved that to 100k, and I'll speed up the simulation because it takes a while for this to settle, but already we're looking at 9.9, but we're not quite at 10 volts, are we? So let me increase the simulate, and you can see that it's now climbing up to 10 volts. That is the machinery of this simulator at work, and it does take time to, as it were, catch up with a step change that you might make. And we are, at the moment, we are 0.002 of an error on 10 volts there. We were spot on at 5 volts, but we got a very, very slight 0.002 of a volt drop. There's a little bit of non-linearity creeping in, only in a very, very small way, considering that this is a fairly unrefined circuit. And we've got this very simple AC amplifier stuck in the middle of it. Now, having taken that to 10 volts, I'm going to move it down to 20k, which is here. And you can see immediately that the DC voltage on the output of op amp B has dropped down to 2.001. So you've got a slight error there in this simulation of 0.001, and now it's settled on 2. And I bring the simulation speed down so that it's a little bit more pleasant to look at. And incidentally, isn't it quite remarkable that this simulator can show you the flow of electrons in all the circuit parts? And of course, you've got, where you've got greater flow of current here in the reference, you've got these electrons whizzing through this. It's very graphical and outlines how fascinating electronics is. There we are. That's the dynamic circuit diagram of this DC amplifier chopper. The history of this technology actually goes back to almost the dawn of electronics. I can trace it back to the 1920s and 30s. And what they had there, of course, they didn't have chopping MOSFETs the way we have today. What they used was contacts, relays. And all they could do is, with a valve, is produce AC amplification, which is this block here, and with a reference voltage here, which probably constituted 2 resistors, they would chop the signal up and amplify it through a little valve amplifier. And probably on the output here, they probably put a capacitor or something of that nature. Okay, so now what I do is I move on to the breadboard, and all I do there is just confirm that the breadboard is functioning the same as this simulator. As this video appears to be getting a little extended, I thought I would put the breadboard demonstration stroke confirmation on a separate video, the link of which will be in the description and presented above. Thank you. This is Beamer signing out for now.